Okay, we're ready for our lesson on linear programming, and this is lesson 1.8, so let's get started with a couple of examples. With linear programming, we are given a system of constraints, so it's a lot like what we were doing when we were solving systems of inequalities using the graphing method. So there'll be a little bit more included, and we'll talk about this objective function provided here up in the right-hand column or right-hand side of the screen. But first, let's go ahead and graph these three different inequalities. And so that starts with this v, y is greater than or equal to the absolute value of x minus 2. So that's the parent absolute value function shifted 2 to the right. So that looks like this. Get my line draw tool. And it's going to be a solid V. And when I do the shading at the end, greater than means above the lines, and for V there's actually two lines, so everything inside the V will be shaded, and maybe I can make those just a little bit longer to give them a chance to intersect with possibly other lines. All right, so let's do the boundary line y equals 8. So let me change my line type. We'll change the color. So here is the boundary line y equals 8. And the shading is the less than side, which would be below the line. Sorry, I changed the color on there, but you get it. So here's my blue, and y equals 8, and when we do the shading, we'll shade below. And now we'll do the green, and we can do this one using x and y intercepts. So the y-intercept will be 49 divided by 8. That's 6.125. So the y-intercept is just a little bit above 6. And the x-intercept will be 49 divided by 5. That's almost 10, 9.8. And we can line those up, and that'll be our other boundary line. All of these are solid. Trying to line this up, make sure I get it. Yeah, I missed that one. Okay, so I've got all of my lines drawn, my boundary lines, and now I'd like to just save the shading for last. And so my shading needs to be above the V, okay, greater than the V, but the other two, it's less than the horizontal line y equals 8, which is below, and then it's also less than the green, which is also below. So we're talking about then when we put all the shadings together, the area that they share, where all the shadings collide, is this area right here. Okay. Now, in linear programming language, this shaded region has a name. It's called the feasible region. And there are some interesting, very important points that we get from the feasible region, and they exist where two lines cross, or in this case, you can consider this two different lines because it really is. So at the point of intersection, on the edge of the feasible region, we have what are known as vertices. Okay, so I'm going to point out some vertices for you. I just circled them there. You can see their vertices lie on the edge of the feasible region, and they represent the intersection points of two different constraint lines. These lines that we've just drawn are called constraint lines in linear programming language. All right, so if we were to list these vertices out, we've got, of course, down here we have the point 2, 0. Over here we've got the point, looks like 5, 3. This is negative 3, negative 3, positive 8. And this is negative 6, positive 8. All right, and so the goal of linear programming is to take these vertices and using them in what we call an objective function. So this given function up here has a name. When you see this phrase, I want you to know what they're referring to. This is called the objective function. And the goal of this exercise is to see which ordered pair, when plugged in for x and y, will give us the maximum value, highest value, and then which one would give us the lowest value or the minimum value. Okay, so if you took the time to plug all these in, each one of them one at a time, you should find out that the max value would be negative 10, and that occurs when you plug in the 0.20. So I'm saying you have a max value of negative 10 at the 0.20. You can see if you let x be 2 and y be 0, you're going to get negative 10 as the output. And then the minimum value is going to be negative 105. And that occurs here at this point. If you let x be negative 3 and you let y be 8, you will get an output of negative 105. And so when you do these problems where you're given a system of constraints, you sketch the constraint lines, you do the proper shading, you identify vertices from the feasible region, and then you test those vertices in a given function. And in this case, they wanted us to tell both the maximum and the minimum value. Sometimes you're just supposed to find one or the other. So just check out your instructions and then follow them appropriately. So this would be the answer to this first example. Okay, the biggest thing I think that you should take away from this lesson is the ability to read a real-life word problem, real-life situation, and then you come up with the necessary constraint lines, graph them, and then you can answer a question regarding optimization, whether that's maximizing profit, which is the case in this problem, or minimizing costs. That's also a common optimization problem. So the first thing we normally do is these problems are always going to involve normally two different products. And so our two products in this problem will be tables. So I'm just going to let the x variable equal tables. And let's get a little more specific. Since we're making tables, we'll say number of tables produced. And whatever you decide on, and it really doesn't matter, you could go either way, but make sure you label your axes accordingly. It's important that we can make sense of your graph when you're done. And I'll just go ahead and label the y-axis as the number of chairs produced. So that will be y. Okay, so now that we've got some variables identified, let's see if we can come up with some inequality statements to represent constraints. Constraints are limitations on our ability to make unlimited quantities of either one of these. For example, because who knows why, maybe it's space, maybe it's labor, but for whatever reason, this particular company can make between 30 and 60 tables a day. So I'm going to, over here, this is going to be called my system of constraints. So one of these constraints, we'll just color code them, will be this between statement that my number of tables produced, X is my number of tables produced, is going to be between 30 and 60. All right, then I've got another statement that says I can make between 40 and 100 chairs. So it's very similar. I'm going to say that Y is between 40 and 100. Okay, so we have a couple of constraint lines regarding the number of chairs produced, number of tables produced, and now we've got another statement that says, but if you combine the two, this sentence here says, at the most, we can make 120 units. So a unit is a combination of tables and chairs. So the sum of these cannot exceed 120. And then in these linear programming problems, we always have a couple of what I call implied constraints, because in real life, it's not possible to make negative quantities of any product. And so you're always going to have these. The number of tables produced cannot be negative. They could be zero. We may choose not to produce any. But we're going to have a constraint line that looks like this, and then another one that looks like this. So you will always include these two constraints to show that, obviously, in real life, we will not make negative quantities. All right, so right off the bat, I noticed that I'm dealing with some pretty large numbers, and so I think I'm going to do my axes in 20s. And so this happens from time to time. Just show me if you have to change the units. Just show me like this what these lines actually represent. And so let's take a look at this between statement, the one in blue. If I've got the number of tables that I can produce is between 30 and 60 a day, so this would be 30, about halfway between. And then this would be 60. And so I need, let me get my line draw tool. All right, so a vertical line going through 30. And then another one going through 60. Okay, and then for the chairs, this time we're going to do horizontal lines through 40. And 100. All right, and then I've got this final constraint that basically, if you think about intercepts, you would have both x and y intercepts would be 120. So there and there, and then I'll try to connect those. Okay, I think I got it. All right, so let's see what we got. Now we'll do the shading. And so we're between the blue, we're between the red, but we have to be below the green. So when we put all that shading together, we're talking about this area right here, maybe a little bit smaller. So this is called our feasible region. And from that feasible region, so now that we've identified the feasible region, let's go ahead and list out our vertices. So I'll just make a little circle here to indicate where vertices are located in this problem. Remember, it's not just the intersection of two lines, it's where two lines intersect on the edge of the feasible region. So make that distinction when you're coming up with vertices. So here's a point, and remember this is 30. So we'll start down here on this bottom left point. That looks like it's 30, 40. So what that means in this problem, it's a combination of 30 tables and 40 chairs. Tables X, chairs Y. All right, and then over here we've got 60, 40. Combination of 60 tables, 40 chairs. And then right here, we've got 20, 40, 60, 20, 40, 60. That's 60 of each. And then up here, this looks like 30 and 20, 40, 60, 80, 90. Okay, so you'll always be told information about how to make either a profit function or a cost function, and you're always interested in maximizing profit. So the information we're given in this problem for profit is we make $150 on tables and $65 on chairs. So our profit function, I'll just call it P, is 150x plus 65y. And now, to optimize, we're just going to choose these ordered pairs, and we're looking for the ordered pair that gives us the highest number for P. P stands for profit. And so you could take the time and plug these in one at a time, see what the output is for these given inputs for X and Y. But to save you a little bit of time, the one that actually gives you the highest value for P is the 60 tables and 60 chairs. And then we're supposed to say, well, how much would that profit be? So let's see what this output is. So grab your calculator. And it looks like that profit number is $12,900. So the two questions that we answered, how many tables and chairs should be made per day to maximize profit? Well, this 60 of each, you can just say it that way, that's the combination that maximizes profit, and then this is our max profit. All right, very good. Okay, so let's take a look at another example, and this one I just broke up into questions to kind of help students with a partner work their way through to building the system of constraints and then coming up with the objective function. And so this is another maximize profit problem. And so let's just walk our way through each of these questions. And I think seeing how these questions are set up, this is a way to maybe help you when you do these on your own, come up with the system of constraints. So a little different problem here. We have a farmer who's growing two different crops. As you can see, the typical way these problems work is you've got two different products, or in this case crops, that we're trying to determine the proper combination of in order to maximize profit. So we have a constraint as we kind of piece our way through this. Well, first of all, let's identify variables. So I'm just going to say my X variable is going to be acres of corn. And then the Y is going to be acres of soybeans. Okay, and then I just gave you a tip here on letter B. You could just go ahead and do that all in one step, but a lot of people forget. They forget to identify their axes accordingly. So let's just go ahead and do that. Number of acres of corn. All right. So we've done this. A farmer has at most 500 acres. So this is describing a constraint. Okay, just think of a constraint as a limitation. He doesn't have all the acres in the world to work with. So this is what he has to work with. So knowing that these variables represent acres of each crop, we can write an inequality that says the sum of the acres of corn and soybeans cannot exceed 500. So we would say less than or equal to 500. All right, so that's the acreage constraint. And now we've got another constraint based on the fact of cost. He only has $12,000 to spend. So we cannot go over 12,000. That's another way of saying he has a limitation on the amount of money he has. We're told that it's costing $20 per acre of corn, so $20 times X. And it costs $30 per acre of soybean, that's 30Y. And his limit, the constraint, is $12,000. Less than or equal to 12,000. Okay. So the additional constraints are these implied constraints to show that it's not possible to produce negative quantities of either crop. So these will be typical of your linear programming problems. You'll just set each of your variables greater than or equal to 0. And now let's just take a minute and put our constraint lines on the graph and do the proper shading. So obviously, we're going to need to change our units. So I'm just going to make each of these axes in 100s. Each line represents actually 100. So for the line, let's do that in blue, this acreage constraint line, we have an X and a Y intercept of 500. And we'll connect those. Running start. So, oh, I think I missed it. Let me try that again. Okay. And eventually that's less than, we'll be shading below. All right. So maybe we'll do the cost constraint in red. So the x-intercept is going to be 600. If you divide by 20, it's 600. The y-intercept is 400, dividing by 30. So 600 on the x. And 400 on the y. Connect those. All right, so let's get a running start on this one, and it's that one too. Boy, I'm not doing too well here. Okay, got it. And now I'll just do these implied constraints. We have, this is our boundary line for x equals 0. Here is y equals 0. And we'll shade the greater than side of each of those. So it turns out that our shading should be right in here, less than the red and the blue, and then the other two greater than, so it confines our shading in quadrant 1. All right, so let's pick out our vertices. So there's a vertex 0, 0, that's no acres of either crop. We have 500, 0, 500 acres of corn combined with no acres of soybeans. We have this 300, 200, 300 acres of corn, 200 acres of soybeans. And then we have no corn acres and 400 acres of soybeans. So those are our choices. So we've done this, and we've I've identified the vertices, the profit function, calling it P for profit. We're told that the profit on each crop is $50 for corn and $65 for soybeans. 50x plus 65y. And now that we've identified the vertices, now it's just a matter of plugging these in, and we're trying to find out which combination of crops gives us the highest value for P, highest profit. And that's pretty easy with the calculator, and what you're going to find out is the one that does give you the highest value, highest number for profit, is the 300 acres of corn combined with 200 acres of soybeans, and then that profit number, let's grab my calculator, and then 65 times 200, and try that again. I think all right, and that is 28,000. So let's fill in this blank. 300 acres corn, 200 acres soybeans, for a maximum profit of 28,000. Okay, so that's the other example that I wanted to walk through with you that we did in class today. And then you're about ready to practice. I just wanted to give you some help on setting up this particular word problem. In the past, I've had a lot of questions about this one, so I thought, well, let's just go ahead and see if we can get it set up for you. And the more of these you do, the easier it's going to become. So once again, we're looking, first of all, we got to identify some variables. So let's see what it is that the question is asking for. Find the number of day shift workers and night shift workers that should be scheduled to minimize cost. So this is going to be a minimum function. We're going to have a cost function. And then we got to find out eventually, well, what is that minimum cost? So I'm just going to give you the system of constraints, and then I'm going to turn it over to you to let you do the graph and come up with the vertices, come up with your cost function. And I think, though, if you can, if you know what the system of constraints is, the rest of this shouldn't be too bad. All right, so I'm just going to define some variables. So I'm going to say X is the number of day shift workers. So when you do your graph, that's how you'll label your x-axis. Y will be the number of night shift. All right, so let's see what we got here. At this theater, we have overlapping 8-hour shifts from noon to 8 p.m. and from 4 p.m. to midnight. And so a lot of our information is going to be taken from this table. So let's see, as far as strictly day shift workers, okay, just the number of day shift workers, that's noon to 4. It looks like according to that, we're going to need at least 5. So I've got a constraint line. So here's my system of constraints here. I'm going to show that I need at least 5 day shift workers. Noon to 4 is strictly day shift. Okay. One of the reasons why I wanted to walk through this, when you might not know, well, where does the day shift, night shift break off point? Well, typically it's around 5 o'clock. From 5 on, in their case, it's 4 o'clock. So what we have here, these are all day, but here is a combination of day and night. These 5 o'clock generally is still considered day shift. So we've got a few day shift workers finishing up, and it's almost like night shift coming on. So there's a period of time where day and night shift overlap. They work together in this 4-hour period. So this is going to be one of these addition. If I take day and night together, combined, day shift and night shift, I need at least 14 during this period. All right, so we have an inequality to represent this period of time, this period of time, and now this is strictly night shift from 8 o'clock to midnight, and we need 6 of those. And then we've got the constraints that we typically have with linear programming. We will not have negative quantities of either one of these. Okay, so that's the system of constraints. I'm going to let you graph it, and then let's go ahead and come up with the cost function, because this one takes a little bit of thought as well. So I'm going to call this C for cost. All right, so what are we told? These workers are going to cost us, as the movie theater, they're going to cost us $5.50 per hour per worker. Okay, so think about that as we build this cost function. Well, this is a 4-hour shift, and we're paying $5.50 per hour for every day shift worker. Okay, then we've got to take care of this overlapping day-night shift period. And these guys, if they're working in this period of time, this 4-hour period, they're making $7.50. So 4 hours, $7.50 an hour, and we represent these people as a sum of day and night shift. All right, and then finally we've got this 4-hour period that's strictly night shift, and they get also $7.50 an hour. But we've identified the night shift workers with the variable y. Okay, so let's just go ahead and clean this up. We'll say C equals, this, if you need to grab a calculator, 4 times 550. So that's going to be 22x. And then we've got 4 times 750. That's 30 times x plus y. And then 4 times 750 again, that's 30y. So taking it one more step, because we can distribute here, let's just think about this as 30x plus 30y. And now come up with a like terms combination. So 22x plus 30x, that's 52x. And then 30 plus 30y is 60y. So we've got you set up really well for this problem. Graph your system of constraints, do the shading, come up with your vertices. This is your cost function, and you're coming up with the minimum. So now you want the lowest value, lowest cost, and what combination of workers would produce that lowest cost. So tell me what the minimum combination XY that produces the lowest cost after you do your graph. All right, so hopefully that helps you with number 26, and you've got the assignment there, and if you have any questions, let me know.